In today's session, we will discuss the important role technology can play in examining road user behavior to predict collisions. Ali will first explain the challenges practitioners face when relying on traditional collision studies and demonstrate the power of video-based surrogate safety techniques. He will then present a few examples of how road agencies are using this technology to identify real issues affecting safety and gaining immediate insights to evaluate the effectiveness of road treatments in weeks instead of years. We will save time to answer your questions at the end of the session. Please type them into the question box as we go along. Before we get started, we're going to launch our first poll question. So please answer the question that pops up on the screen. What type of data do you mainly rely on for road safety studies today? I will now hand it over to Ali to kick things off with the presentation.
Thanks, Julie. And hello, everyone, and thank you for joining us today. Looking at the crash statistics worldwide, road crashes kill over 1.3 million people and injure up to another 15 million people each year. You may be already familiar with the concept of Vision Zero. Vision Zero is a strategy to eliminate all traffic fatalities and severe injuries. Vision Zero assumes that while it is understandable that many crashes happen mainly due to driver error, traffic fatalities and injuries are preventable based on the 5 E's approach: engineering, enforcement, education, engagement, and evaluation. For any of these 5, we need to first understand how safe or unsafe a location is. But crash data are not ideal source of information, at least up to this present time. This is because first, not all the traffic crashes are reported, a phenomenon called underreporting. This is frequently the case for no injury and minor injury crashes. This can limit the ability to manage road safety since most of the analyses are based on reported crash data. Also, crashes, of course, fortunately, are quite rare. Because of low sample size, it is often too difficult to draw solid conclusions from safety analysis, especially at individual locations which we have very limited data for crashes. In addition to rarity, crashes are complex events in a sense that they are caused by multiple factors or multiple failures. The information preceding each crash is usually quite limited. This limits the possibility for drawing inferences about the complex chains of events leading to the crash. Last but not least, there is an ethical point in using crash data. Using crash data is a reactive approach. We need to wait until a sufficient number of crashes unfold before hazardous sites or situations can be identified and then be corrected. That's why the use of a more proactive approach is preferable. Without a proactive strategy, we cannot actually get ahead of dangerous traffic situations, and we can only address problems after it's too late for some people. Instead of using crashes only, we can use surrogate measures of safety. Accurate and quick measurement of safety with surrogate measures offers a viable solution for the issues associated with crash data. Here we can see some examples of surrogate safety measures. For example, maximum speed, maximum relative speed difference, time to collision, post-encroachment time, deceleration, and some other safety surrogates. Traffic conflicts is the most widely used surrogates of safety. Traffic conflicts and crashes are believed to belong to the same family, but with different severities. this idea in mind, using the first traffic conflict technique dates back to more than half a century ago. A traffic conflict naturally precedes each collision. In fact, we can say that each collision is a result of a traffic conflict, which the risk of the collision was impossible to be avoided. Thus, traffic conflicts are potential collision situations, and their types predetermine the types of collisions. In other words, if we see a particular type of conflict happening on the road frequently, it's very likely to have the same type of collision. As it turns out, we can learn a lot. Serious near-miss events or traffic conflicts unfold on the road every day. Here is an obvious example. These events are considered collision precursors since they contain most or all the necessary ingredients that are required for a collision to unfold. Why not look at them in addition to crashes? As I said earlier, naturally we expect to see more crashes unfold, where we also see more collision precursors. More importantly, if we remove the factors that lead to collision precursors, we can eliminate collisions altogether before they happen. This data doesn't take years to collect, and we have the opportunity to collect it before a single serious crash happens. Now I will talk about how our technology generally works and how we can use it to improve road safety. Our process includes 3 stages: detection, tracking, and analysis. I will elaborate on each of these on the following slides. The first step in video-based safety analytics is road user detection using computer vision. The software takes the video as an input and tries to do what the human eye would do, that is to see or to detect the different road users in each frame of the video. The road users are classified into different types like cars, pedestrians, trucks, buses, based on their visual characteristics. And these numbers are showing the algorithm's levels of confidence in determining the detection. It's noted this can be done for different locations such as highways, intersections, roundabouts, and so on and so forth. Also, all road users, including micromobility such as e-scooters, bikes, they all can be detected. Here we can see an example for a drone video that was for a roundabout in California using the videos obtained from, as I said, drones. The second step in the process is tracking. In this step, we use the data generated from the computer vision-based detection and transform it into positions and velocities at each frame of the video. In this stage, we also try to reduce the amount of noisy detections. The generated trajectories allow precise movement classification and provide accurate movement counts for all modes of transportation. There are 2 views for displaying the data: camera view and bird's eye view, or a map with known GPS coordinates. As we can see, we can have different types of road users separately detected, and for different movements like east crosswalk, north crosswalk, south left turn, and so on and so forth. Using the trajectories that contain velocities information, we can plot the following speed heat maps and get the insights from them. The points here represent the mean speed of the conflicting vehicles. For example, we can see at the center of the intersection, we have drivers that travel with higher speed compared to the approaches that the speed is around 15 kilometers per hour or something. Video analytics software can capture all types of traffic interactions. For example, we can see it again. A conflict for two vehicles traveling on the same direction, and a conflict between two left-turning vehicles. Here also we can see two examples for the conflicts that involve vulnerable road users. This one is for a city in Netherlands, and this one is for Belgium. As I said earlier, all types of interaction between road users can be identified and detected using video analytics software. Figures can be plotted to highlight the dangerous locations. Each point on the figures corresponds to a safety-related event. In this example, the events are all PET, or post-encroachment time. We can see that the pedestrian scenarios here are more critical because they have a lower value of post-encroachment time. And at the center, which is intuitive, the PET is higher, showing that it is less critical compared to the crosswalks for this particular intersection. Another output of the analysis section is speeding violations detection. We observe when road users go over the speed limit during their detection, similar to a speed radar. Using the movements classification, we can observe which movements are more likely to have speeding compared to the other movements. With that, I'll now pass it to my colleague Julie for a poll question.
Thank you. So the second poll question is, what type of conflict or violation data are you most interested in tracking? So it looks like most people are interested in tracking conflicts and interactions between motorists, as well as conflicts involving vulnerable road users. Thank you for sharing that.
We'll continue by discussing road safety management process. The process seen on this slide shows a typical practice for road safety management, which includes 6 different steps or parts. Depending on the country or region, some steps can be combined together or have some subsections, but the whole idea is more or less the same for any region. Surrogate safety analysis can assist transportation professionals in at least 4 of these categories. With network-level coverage, our automated tools help you quickly identify the most problematic sites in your network screening. It's like triage on the network to quickly find where the dangerous sites are located. Once you have determined which sites to study and get more information, which sites we need to get more information for them, our technology can be used as a screening tool, allowing engineers to easily identify the most problematic movements or situations or scenarios, to observe the mechanisms involved. This is done by reviewing the videos of the most serious traffic interactions extracted from the videos. It's like an X-ray on the intersection, for example. Our technology also assists in countermeasure selection by linking the observed challenges to treatments available in CMF Clearinghouse website, a website under supervision of Federal Highway Administration. So when we find a problem, that can link you to the potential candidates for the countermeasures to address the problem. And finally, revisiting the intersection with a follow-up after a study, it can help identify whether the countermeasure is effective or not. Most importantly, potential problems can be captured much more quickly, which leads to have a much less risky implementation of the treatment. For example, if the treatment doesn't work in a way that we wanted, so we can find it as soon as possible. Regarding the first one, network screening, it may be already familiar to you if you've done AADT estimations based on permanent sites. For example, the city of Bellevue in Washington leveraged their existing network of traffic cameras to continuously monitor 14 intersections for their network. These were some critical intersections that they had some highlighted crashes. So these 14 intersections were then analyzed based on different measures, not only AADT, but also other measures like the safety indicator or the amount of speeding at the intersection. This gives you a much more detailed idea about the safety of your network compared to relying only on traffic volume. In the second step of road safety management process or diagnosis, the system automatically identifies the different scenarios, combinations of movements and road users, and it highlights the most problematic locations, scenarios, situations, or time of day, which one are more critical. Videos like this can be reviewed to get a better understanding of the mechanisms behind the most dangerous interactions, which helps engineers identify common themes and problems unfolding in the field in a real video. These are not simulation. We just see how the conflict, how the dangerous conflict looks like. This also comes with a great deal of rich and granular information, which provides aggregated data visualization layers. As another example, we conduct a project for Vic Roads, the state agency who manages roads in Victoria. The objective was determining the most prevalent types of traffic conflict. So we can see, for example, this one was very frequent for that particular intersection, and the detailed information about the dangerous scenarios such as vehicle types and exact location of each interaction was also provided. As another case for diagnosis step, here is a drone video observation that was used for a rural intersection in California to identify the contributing crash factors, collecting a total of 34 hours drone video footage at this site, where it was challenging to mount fixed cameras. It was possible to get an accurate picture of the potential crash factors. Besides the detected traffic conflicts and conflict videos, engineers were able to rely on trajectory images and speed heat maps like this, allowing the divided highway as well as for the crossing movements. For instance, for this project, there was some concern about left turning movements, and they hired a GHD company to study driver behavior, to better understand driver decision points, congestion, acceleration, and speeding, as well as peak hours. So, as GHD's project manager stated, the near miss and speed data played a big part in validating the need to close the existing highway left turns and the subsequent optimal locations for the proposed improvements needed to offset the impacts of the restricted turning movements. The data furthermore helped with determining the specific alternative options and geometrics at this stage. Regarding the third part of road safety management process, countermeasure selection, so these can be related to, can be linked to the website, can be linked to the website under supervision of Federal Highway Administration or CMF clearinghouse to get the potential CMFs, or it's better to say the countermeasures that we can employ when we find the problem. This can save time when performing step 1 to 4 of the standard CMF selection guide. But this technology is particularly popular with traffic engineers and practitioners because how easily it can be used to study the effectiveness of the implemented countermeasures. If you want to change something on a road or intersection, you don't need to wait several years for crashes in order to realize how your change affects the safety of the location. You can just check the critical events or traffic conflicts before and after the change. In the following slides, I'll show you some examples how our technology has been used in different parts of the world for before-after studies. Beginning with the first one, the city of Toronto in Canada was interested in finding the effects of reducing curb radius with the intention of reducing the walking distance of the pedestrians, and at the same time reducing the amount of the travel speed of the conflicting vehicles. So while it is theoretically interesting for improving safety, there is very limited evidence that this strategy is really helping the safety of the road. So instead of waiting for years, our analysis showed that the curb radius reduction reduced conflict rates and the speed of turning vehicles involved in the conflicts. For example, there was a 30% reduction for the rate of the conflict for the high risk, and there was a higher reduction for a low risk conflicts, as well as the reduction that we saw for the speed of the conflicting vehicles compared to the before situation. the City of Toronto appreciated the quick and predictive nature of the collecting data on safety-related events using video footage. Therefore, they have deployed this technology at many other intersections, including a first of its kind, a lift-term calming pilot at 10 high-risk sites across the City of Toronto. This video in Netherlands shows a conflict between a vehicle and a cyclist. You can see it again. It was a project that was carried out by SWOV, the Dutch Institute for Road Safety Research. This study focused on evaluating various interventions on the built infrastructure, aiming to increase cycling safety. Here you see the trajectories for the before scenario on the left side and after scenario after some interventions at this intersection. So we can see the trajectories as a case in point. The trajectories for north through cyclists have been changed significantly after this. We can get much more insights from these trajectories and other granular information that we provided for the city. As the last example for before-after studies, in Lower Hutt City in New Zealand, the city had this three-legged intersection with this interesting geometry. In an effort to improve pedestrian safety, the city changed the pedestrian crossing from only zebra stripes to painting them a vibrant red color. This made the crosswalks more visible for oncoming vehicles. The city was very pleased with the results the countermeasure had on safety, which these results were not easily quantifiable without the use of our analytics. In terms of critical conflict rates, a decrease of 29% was observed for all the traffic conflicts, and a significant reduction in the conflicts for pedestrian was observed. For the critical conflicts rates, and for the minor conflicts rates, we also saw some reductions. For the speed of the conflicting vehicles, we also saw a reduction for 2 roads among the 3 roads investigated. So, in general, the treatment was found to be very effective, and the city wanted to consider it for the other intersections. With that, I pass it to my colleague Julia King. Sure.